Welcome to Part 2, Atomic Theory Notes. Today we are going to talk about three models: Rutherford, Bohr, and the quantum mechanical model. The gold foil experiment that led to Rutherford's model begins at Thomson's lab. Thomson's student was Rutherford. When Rutherford graduated, he wanted to test if Thomson's model was true using the latest technology. So he asked, is the plum pudding model correct? At the time, they have discovered a radioactive element that emitted alpha particles, which were positively charged particles, basically helium nuclei. So he wanted to ask the question, what would happen if you shoot these alpha particles that are positive at individual atoms in a thin piece of foil, metal foil, like gold foil? So his hypothesis was that most of the alpha particles, the positively charged particles, should go right through the gold atoms as shown over here, if Thomson's model was correct. And there would be hardly any deflections where these particles would come right back at him. So here is his setup. Before I explain this, I'm going to pause and go to a video. So this is the setup that was used for the gold foil experiment. A radioactive isotope was placed inside a lead container with a small hole where the radiation can come through. And there was another piece of lead with a tiny hole so that only thin beams of that alpha particles will come through. And in front was the gold foil shown over here. It was very thin, so it had very small layers of gold atoms, and it was surrounded by a zinc sulfide coated screen. So they added zinc sulfide because when you can't see these alpha particles, but when they collide on the screen, you see a spark. And you could count the number of sparks and where the directions of the sparks were. So when the beams start coming, most of the beams went right through as they expected. But a few, as you can see, would go in small deflections, and some, like that one, made a large deflection. So in all, he found that 99% of them went through. 1 in 20,000 came right back at him. So based on this experiment in 1911, Rutherford came to the following conclusions. First, the radioactive sample emitted a beam of alpha particles that is heavy and positively charged, and the majority of it went right through the gold foil. And 99% of it produced flashes of light right on the opposite side, on the silk sulfide screen, showing there was no deflection as he expected. But unexpectedly, there were some minor deflections that were seen occasionally. And then 1 in 20,000 deflections were major deflections. They came right back at him. Now, alpha particles are positive. The only way a positively charged particle would be deflected is if it hit something that is positively charged inside the atom. And since these collisions were so rare, Rutherford decided that there must be something very tiny and heavy at the center of atoms. And he called this positive, tiny, heavy center of the atom region the nucleus. So let's look at the observations and the conclusions he came to. 1 in 20,000 alpha particles were deflected back because they are very heavy. So he concluded there is a tiny but really heavy region he called the nucleus in the center of an atom that deflected alpha particles. Please note that he has not discovered the positively charged particles yet. Number 2, the nucleus is positively charged because it repelled alpha particles that are positively charged. Only like repels like. And then second, most of the alpha particles went right through like this, the gold atoms shown here. So he decided most of the atom is empty space. Now for the first time, atoms are not thought of as solid, they are mostly hollow. Please write this down in your notebook. So let's review Thomson's model and the Rutherford model. The positive charges that were spread out all over like the dough that holds chocolate chips is now concentrated in this tiny space. And around that you have the electrons. And between the electrons and the nucleus is all hollow space, not something like dough. So Rutherford's model is called the planetary model. Now there were some other things you need to know. In 1914, Rutherford discovered protons. He discovered particles that travel in the opposite direction of cathode rays. They were going from the anode to the cathode in a cathode ray tube. He called these protons. Now these are the particles that were deflecting the alpha particles in the gold foil experiment. Then in 1923, Robert Millikan calculated the mass of an electron using the oil drop experiment. And then in 1932, James Chadwick discovered neutral subatomic particles called neutrons. There was an issue with Rutherford's model, and he couldn't explain, like what is shown in this image, why when metals absorb heat energy, they start glowing, and then once they lose the heat energy, they go back to their cool state without any glowing. Now, Rutherford student Niels Bohr wanted to explain this. Now, if you think of a specific amount of energy like this, let's imagine this is 100 units of energy. It's not one continuous piece of energy, unit of energy. It's made out of tiny quantized packets as shown here. And you can think that it's like money. If this was $100, it's made out of a lot of pennies. So money is also quantized. So Niels Bohr wondered if energy inside the atom was also quantized. At the time, in 1901, Max Planck proposed that all energy was quantized and matter could emit or absorb energy only as units known as quanta, like a small unit of money or small unit of energy. And then in 1905, Albert Einstein explained the photoelectric effect, where when sunlight shines on certain metals at a certain frequency, electrons are ejected from the surface of the metal and an electric current can be produced. This is how solar panels work. Anyway, it was interesting to note that only certain energies of light can eject electrons out of these metal atoms. So, Niels Bohr proposed a modification to Rutherford's model. He didn't do any experiments, and this model explains how metals glow when they are heated by including a quantized energy into the atoms. So let's look at Niels Bohr's model. he put electrons in specific energy levels. They were not all arranged around the atom in one energy level. They were in specific locations. He called the distance between one energy ring of electron circulation and another a quantum. So he said electrons are found in specific circular paths called orbits. So here are two orbits. They are also called energy levels. These have quantized energy. A quantum is the amount of energy needed to move an electron from one energy level or orbit to another. So for example, when you heat a metal, the metal electrons will absorb that energy and jump from a lower energy level or orbit to a higher one. Now, higher ones are located further away from the nucleus. And he said when gaining energy, electrons move to further orbits from the nucleus. And then conversely, when losing energy, electrons move to an orbit close to the nucleus. Finally, we are going to the quantum mechanical model of the atom, also known as the Schrodinger model. Schrodinger suggested that, based on mathematical calculations, that electrons move in wave-like motion around the nucleus, not as the particles they were thought of being. According to Werner Heisenberg's uncertainty principle, the location and the velocity or speed of electrons that are moving around the nucleus can't be measured exactly. So when you put these two concepts together, you have the modern view of the atom, explaining the location of electrons as a cloud region, not as specific orbits or anything like that. So they are in a cloud-like arrangement around the nucleus. In the quantum mechanical model of the atom, Bohr's orbits are now replaced with orbitals. And orbitals are three-dimensional regions of space with a high probability of finding an electron. So the modern atomic theory was influenced by the work of Heisenberg, Schrodinger, and Bohr. And here's a summary of all of the two models. Here is Niels Bohr's planetary model and Schrodinger's quantum mechanical model. It has, by this time, protons, neutrons, and electrons were discovered, so the nucleus has both neutrons and protons, whereas the electron cloud is this hazy area around the nucleus. And here are all the atomic models: Dalton's model, Thomson's model, Rutherford's model, the Bohr's planetary model, where electrons are in quantized energy levels known as orbits. And then in the Schrodinger model, you have the electron clouds. And that's it. I will see you in the next lesson. Please do the exit ticket.